Okay, here we go. Getting close to the end. Chemistry 3202 review. This is Lesson 3, Electrolytic Cells. Okay, you're going to need your standard reduction table again in this lesson. So again, if you don't have it printed off, you may want to go to the tables and charts link there on the home page and print off the standard reduction table. The one with the markings is the better one because I have some things written on that for study purposes, I guess. So here we go. Okay, we're going to be looking at electrolytic cells, and this is covered on page 776 of your textbook. And there's a few related textbook items there you can give a try, and don't forget to have a look at some of the public exam items on this as well. Okay, so we're going to look at electrolytic cells this time. I got a little picture here of some lemmings. These guys are all rushing to jump off the cliff there and jump in the water. Once one goes, they all go. So we're going to have a look at that now in a sec. And here we go. Okay, now we were looking at electrochemical cells last day, and we were saying that when we hooked up two different half cells, if we could calculate the voltage and the voltage turned out to be a positive value, then the way we had it set up with the anode was the one that was going to produce the electron. So we could figure that out by determining the voltage of the cell as it was set up. And in that case, E was positive. But what if we set it up and we had the anode set up such that when we did our calculation for E, it turned out to be a negative value, and when we tried to hook up our electrochemical cell, it didn't work. We didn't get any voltage from it. And of course, the reason for that was that we had it hooked up backwards such that the electrons were unable to fall in the direction that we wanted them to go in because our anode was no longer the one with the highest energy, but it would have been the one with the lowest energy. So what we set up, of course, was something that was not going to work. However, if we could kind of reverse the procedure here by providing some energy ourselves, like recharging a battery, you know how our cell phones and iPods go dead, we have to plug them in to recharge them. Well, essentially that's what's happening. We're energizing the cell once again. And that's what we're doing in electrolytic cells. All right, so let's have a look at what an electrolytic cell is going to behave like. So here we go. It's pretty much the same as an electrochemical cell, except that we know now that when we calculate E with the anode and cathode set up in that direction, that the E cell is going to be negative. All right, so we're trying to reverse the flow of electrons. So in other words, the electrons, instead of flowing down, we're now going to push them up, all right, with energy. So we would refer to this as a non-spontaneous cell, in which case the electrons are not going to move. And okay, we're going to get a negative cell potential. The second thing here is that the polarity of the cells are going to be reversed. In an electrochemical cell, the side that produced the electrons, there was a surplus of electrons on that electrode, so that became a negatively charged electrode. So in that sense, in an electrochemical cell, the anode was negative. In this case, we're going to reverse the flow of electrons. So we're going to get a buildup of negatives on the electrode where we're going to see reduction. So in this sense, the cathode, the site of reduction, is now going to be negative because we're going to start building up negative charge on that particular electrode. This will become a little more clear now in a second when I do an example. So we see a reversal of the polarity. And the third thing we have here is we don't necessarily need a salt bridge. Some of these electrolytic cells, you can use salt bridges, but in many of them, a salt bridge is not necessary. And of course, the purpose of the salt bridge in the electrochemical cell was to try and maintain electrical neutrality, because ions had to be moved one way or the other in order to make sure that everything was electrically neutral. In the case of an electrolytic cell, we're going to see that when one positive ion is removed on the cathode, a negative ion is going to be removed on the anode, or vice versa. So we're going to take care of our electrical charge or our electrical neutrality by way of how the electrolytic cell works. All right, so a salt bridge is not necessary. However, in some situations you can have a salt bridge. Okay, so let's have a look at one. This was first studied by a fellow by the name of Davy. And what he was looking at was he was saying, okay, let's take some sodium chloride and we want to break it down into its ions. Now, there's two ways we could do that. We could take the sodium chloride and dissolve in water at room temperature. You know, like you're going to boil some potatoes or something, you might throw a bit of salt in the water. All right, but the problem there is water is present, so we're going to have some other substances in that solution that could possibly interfere with the flow of electrons. And in the case of water, we're going to talk about that later on. So Davy didn't want to have anything other than sodium ions and chloride ions. He does not want any water there to interfere. So what he did was he took some sodium chloride solid and he melted it at 800 degrees Celsius. About 803 degrees Celsius is the temperature that the ionic crystal lattice of sodium chloride begins to break apart. And we start to see the production of sodium ions and chloride ions in the liquid state at 800 degrees Celsius. This is extremely hot. Do not touch. All right? Very, very hot. This is so hot, in fact, that you can't really generate those temperatures on a regular household stove. So you'd never be able to melt sodium chloride yourself. All right? So it would have to be extremely hot here. So what he did is he simply took a very heat-resistant container here. All right? Now this is going to be simplified, no doubt, compared to what Davy did. But if you want to check out how he did this, just check out the diagrams on page 776 of your textbook. So we're going to simplify this. So what he's going to do is he's going to take this vat here, and he's going to put two carbon electrodes, inert electrodes, down in the container here. And what he's going to do is he's going to put some sodium chloride solid in here, and he's going to heat it up to 800 degrees Celsius. So this is going to be over 800 degrees Celsius. And what's going to happen, of course, is the sodium ions are going to be in the liquid state, and we're going to get some chloride ions in the liquid state. Notice how I'm not writing AQ. AQ refers to the presence of water. That's not what's happening here. We're simply disintegrating the ionic crystal lattice by melting the structure. So we've got free sodium ions in the liquid state, very, very hot. We've got free chloride ions floating around here, very, very, very hot. What he did then was he set up this and he applied an electric current. All right, now this symbol that I'm writing up here is a symbol to represent a DC current or a DC battery. All right, so direct current. And the little stroke and the long stroke, the little stroke represents the negative terminal of the DC power source or battery. So what he's going to do is he's going to hook that to this side, and then he's going to take another piece of wire and hook that up here. Now, what's going to happen here is when we flick the switch and the electrons begin to flow, the electrons are going to flow away from the power source in this direction. All right, because the negative terminal of a battery or a power source, the negative terminal is the source of electrons. So electrons are all being pushed on here. And just like the lemmings, these guys want to do something, so they start piling up and crowding around on this electrode. And hence the diagram of the lemmings. Let's go back and look at the lemmings. There you go. Right there, look, these guys are all crowding around trying to do something. All right, so they're like the negative electrons here, all crowding around on that piece of carbon, trying to do something. All right, so they crowd around on that, and as what happens here is this electrode now takes on a negative charge. So if that piece of carbon becomes negative, what's going to happen here is it's going to attract the positive ions in the solution. So on that particular electrode, that graphite electrode, what we're going to see is the reduction of sodium to produce sodium metal, which is going to be in the liquid state because it's going to be very, very hot. Okay, so sodium metal in the liquid state. This, by virtue of the fact that it's gaining electrons, is reduction. And we know that the site of reduction is the cathode. The cathode is the site of the reduction. So right off the bat now, we know that this guy over here is the cathode, and its charge is going to be negative in this case. So that's what we mean by the polarity has been reduced, because in an electrochemical cell, it was the anode that was producing electrons. In this case, the charge is a result of all these electrons crowding around trying to get a chance to reduce some of these sodiums. But it's not the charge of the electrode that determines its identity. It's what's happening on that electrode. In this case, we're seeing reduction on that carbon. Therefore, it makes it the cathode. And because of what's happening here, the cathode in this case is going to be negatively charged. All right. Now, at the same time, the electrons that are coming from this power source have to make their way back, right? We need a complete circuit in order for electricity to flow. So all these high energy electrons, very high energy, these guys have lots of voltage here. They want to do a lot of work. They go and do their work, and all of a sudden we want to get electrons that are going to start moving back. So electrons that are going to be moving back are being pulled off this carbon rod here. And as a result, because the electrons are being pulled off that carbon rod, this rod is going to be left with a deficiency of electrons. So as a result, this is going to have a positive charge because the electrons are being pulled away from it by this power source right here. And because this graphite rod now becomes positive, you guessed it, now this guy is going to attract the chlorine, in which case we're going to see the oxidation of the chlorine. The chloride ion is now going to lose its electron. That electron that's been lost by chloride now is moving up the graphite rod and back to the power source. So we're seeing the oxidation of the chloride ion here, which means oxidation is now going to be the anode, because we know wherever the oxidation is occurring, that's going to be the anode. So in this situation, the anode has a positive charge because the electrons are being pulled away from it. The electron's going to be electron deficient. And there we go. What we're going to see here is we're going to see chlorine gas beginning to bubble off this electrode. And over here we're going to start to see some sodium metal starting to form. And what's going to happen here, because this is so hot, the sodium metal is going to be somewhat in the liquid state here, and it's going to be able to be recovered in the liquid state. They'd warm it up and they collect the sodium metal and then cool it down afterwards. So there we go. And again, we don't want water being present here, because water is going to cause competition for these electrons. And anytime we have competition for electrons, we've got to watch out and see which way is going to be the easier path. But in this case, that's what's happening. Now, can we calculate the voltage? One of the questions you're probably going to get on the public exam is say, okay, if this is an electrolytic cell, how much voltage is going to be required to get this reaction to happen? And we would do this exactly the same way that we've been doing the calculations for E cell all along. You can do a half cell reaction where you can look up the values on the table and make sure if you're going to do the half cell method that because this is oxidation, you change the sign. The other way we can look at this is, now that we have the anode identified and the cathode identified, we can simply do the formula method where we can say what's going to be the E of this cell, whether it be electrochemical or electrolytic. We're going to calculate it the same way. So it's going to be E of the cathode minus E of the anode from the table. There we go. And make sure you take care of that negative sign there. So negative 271 minus 1.36. And this ends up to be a negative 4.07 volts. Now, is that what we expected? Well, absolutely. Because this is a non-spontaneous reaction, it would not happen. This reaction would not happen if we did not have that power supply to push the electrons in that direction. And the voltage that's required here is a negative 4.07 volts. Okay, now that in itself has some issues here that we're going to look at. If we look at this guy as being an electron, then this is the potential or the push that we have to put in to get the electrons to move up that concentration gradient, or that electrical potential difference. We have to push the electrons up. 4.07 volts is only going to take you from here to here. We need to give you a little tiny kick to get you over. So generally speaking, in order to get that chemical reaction to occur, we need to supply what's called an overpotential. So because the minimum is 4.07, we'd have to supply just a little tiny bit more to get this guy over the top. All right, so it's kind of like a little barrier there, and 4.07 is going to get you there, but we need another little kick to get you over the top, so we would call that an overpotential. There we go. Okay, So this is a description of what just happened in that cell. So quickly, it says the external force from the power supply is going to push the electrons onto one electrode. That's now going to be negative because all those electrons are piling up. As a result of the electrons piling up, it's going to attract the positive ion, which gets reduced here. And then what happens is as the electrons are pulled off the other electrode, that one becomes positively charged, and then we start seeing the oxidation. Okay? And as with galvanic cells, this is true for both of them. Remember, Leo is an ox. Anywhere that oxidation occurs, that's going to be the anode. The other one where we see reduction is the cathode. Okay? The polarity now is reversed from a galvanic to an electrolytic. Okay? And we just explained the reason for that. And the question here is, why must the negative terminal of the battery be connected to the cathode of an electrolytic cell? Whichever side we want reduction to occur on, that's the side that has to be hooked up to the negative of the power supply. And the reason for that, of course, is that the electrons are what's causing the reduction. If we want reduction to occur, then that's the side that the electrons have to be supplied to. Okay, there we go. Okay, here's another example, and this is going to be an example where we're going to take some calcium chloride this time, and we're going to do a similar situation. We're going to make it molten, which means it's going to be phenomenally hot, like way up in the 800 or 900 degrees Celsius. We're going to hook up two terminals, of course, and in this particular cell, we're going to make it very, very hot. So I'm simply going to say hot, hot, hot. Whatever the melting point of calcium chloride would be, we want to get some calcium ions in the liquid state and chloride ions in the liquid state. Now this time I'm going to reverse the power supply. I simply reverse the power supply. Remember that this small portion here, the small line represents the negative end of that power supply. So I'm going to hook it up on this side this time, which means now this side is becoming negative. And it really doesn't matter what side becomes negative, does it? Because whichever side becomes negative, then that's the side that's going to pull the positive ions to. So on this side, we're going to see the reduction of calcium to produce calcium metal. As this proceeds, okay, the electrons are being pulled away from the other terminal. So electrons being pushed down there, they're being pulled away from this one, which makes this terminal positive. And in this regard, we see that now chlorine is going to be pulled over here, and we're going to see the production of chlorine gas on this side. So it's not whether it's left or right that determines which way things are moving. It's determined by what side are the electrons being piled up on. Okay, so in this case, we get the oxidation half reaction. And there we go. So in this case now, this guy, because it's the site of reduction, this is the cathode. And in this case, it's negatively charged. Okay, it's the cathode because it's the site of reduction. The other side, of course, is the site of oxidation. So this is going to be the anode, which is positive. There we go. And if you want to calculate the voltage required here, again, because this is requiring a power source, this is going to be electrolytic. Electrons need to be pushed in order for this to happen. It would not happen. You look up the values for calcium, you look up the values for chlorine, and it's going to be cathode minus anode again, and it works out to be a negative 4.23. That's the voltage required, plus a little tiny bit more to give me a kick. So I'm going to need a voltage slightly larger than 4.23. There we go. Okay. So here's a comparison, I guess, of a galvanic cell with an electrolytic cell. In this case, we've got zinc hooked up with copper. Okay, now I'm going to take this and go to another page here and say, okay, here's the two setups. We've got zinc electrode hooked up with a copper electrode. And in the other case, I got the exact same thing, but in this case, I've got a power source supplied. All right, and this is going to be the negative terminal of my battery. So looking at the electrochemical cell, which is going to produce a voltage, it's spontaneous. We have to look at this and say, okay, which metal is going to be producing electrons? And the answer to that is Zinc is the easiest to be oxidized. It's the one that's lower on the right-hand side of the table. So zinc is going to be the one that's going to be oxidized. So what we're going to see is the electrons are going to move away from here, and we're going to see the production of zinc ions. So in this case, it's the zinc that gets oxidized because zinc is the most reactive metal. As the electrons are coming over here, the copper ions now are going to be attracted, and we're starting to see the buildup of copper on this electrode. On the other side with the zinc, we're going to start to see the zinc disappear. Okay, so the zinc gets used up, the coppers get plating out here, and what we're going to see is the reduction of the copper. So that makes this half cell the cathode. Now remember what we said about the movement of ions in the salt bridge? Potassium nitrate would be in our salt bridge. Anions move to the anode. So in this direction, we're going to see the nitrate moving there, and probably we're going to see the potassium moving here. Okay? Now if we want to calculate the E for that cell, it's going to be E of the cathode minus E of the anode. And because the electrons are free to flow from zinc to copper, this will be a spontaneous reaction, and we end up getting a positive 1.1 volts. It's spontaneous. Electrons will flow. We will see a voltage to run our little iPod here. Okay, now in the other cell, what I want to do is in this reaction, the electrons spontaneous flow from this direction, from the zinc to the copper, from the zinc to the copper, spontaneous. In this case, we've got it hooked up such that we want the electrons to go in the other direction. So this is going to be the negative terminal of our battery. So electrons are going to be pushed in that direction. So in that case, this becomes negatively charged, which now is going to attract the zinc. So the zinc starts to build up here now. So what we see this time is the reduction of the zinc. And again, look what's just happened here. Up here we had oxidation, so this was the anode. Down here we've got reduction, which makes this the cathode. You notice how the negative charges build up here because of the power supply? Whereas up here, the negative charges are building up and trying to get around. Okay, so in each case, we're seeing the buildup of negative charges here, but we got to watch out because this is the anode because of oxidation. This is the cathode because it's the site of reduction. Now the same thing's going to happen here as the electrons are pulled away from the copper. This becomes positively charged, and then that's going to be producing electrons. So we're going to see copper flowing in that direction. And again, as we start seeing this, what's going to happen now is the copper is going to start to diminish in this case because we're seeing the oxidation of the copper. If we do our calculation this time, you notice what just happened here? This guy's copper is the cathode in this reaction, but down here it's the anode. So when we calculate the E cell for this, everything is going to be flipped over. And E cell ends up being, you guessed it, a negative 1.1 volts. So if I want that reaction to be reversed, I have to push the electrons back up the same distance or the same potential that they fell. So in this case, the electrons are falling from the zinc to the copper. In this case, they're being pushed from the copper to the zinc. Same voltage, different sign. This is spontaneous. It will happen as zinc as the anode. This reaction will not happen unless we push it to happen. Non-spontaneous. And don't forget about our overpotential. 1.1 volts is not going to be enough to do it. We'll need a slightly larger than 1.1 volts. Okay, there we go. So a comparison of this side by side, what we're looking at is in the first reaction, we're seeing zinc as the anode. In the second situation, we're seeing copper as the anode. Look at the shorthand notation, right? Anode, cathode. Anode, cathode. So the shorthand notation doesn't change. In this case, the galvanic cell or the electrochemical, of course, it's spontaneous. E cell is positive. In the electrolytic cell, it's negative. The purpose is to generate an electric current in an electrochemical cell. An electrolytic would be for recharging and electroplating. We need to We're going to cause the reduction of a metal, and we'll talk about that now in a sec. Okay, the anode in this case is going to be the zinc, because this is on the anode side in my shorthand notation. And in this case, the anode is going to be the copper. And remember now, the anode is the site of oxidation in both of these cells. Regardless of whether it's on the left or right, we have to look at where is the oxidation occurring. The cathode is going to be the copper, and the other, in the electrolytic cell, the cathode is going to be the zinc. And again, right, cathode is on the right-hand side. In this case, cathode is on the right-hand side. So zinc is the cathode here. In this case, copper is the cathode. The reactions here, oxidation of zinc, reduction of copper. In the other electrolytic cell, we see the oxidation of copper and the reduction of zinc. So everything is reversed. The overall reaction is reversed. Okay, so we see the opposite things happening. And of course, we get the opposite signs for the voltage. And don't forget here, we need an overpotential to get that to work. Okay, there we go. All right. Okay, now what about water? We talked about before, what if water is present? Everything we've done to this point, we said we had pure ionic compounds and we put them into their very high melting points and we liquefied them to get the free ions to float around. Now we said, what happens if water is present? Well, if water is present, if we had some pure water in this container with no other impurities, no salt, no nothing, pure water, the only thing that's here is pure H2O. All right, so H2O pure. And if we pass an electric current through these two inert platinum electrodes, what we notice that we start to see bubbles forming on both of these guys. And we start to see twice as much gas in one as we do in the other. And that's a telltale sign to say what's going on in each of these test tubes. In one test tube, we're seeing the oxidation of water to produce oxygen. In the other test tube, we're seeing the reduction of water to produce hydrogen gas and hydroxide ions. Now, how do we know which is which? Well, if we want to balance this for the number of electrons, I'd have to multiply this equation by 2, so that I would get 4 water here now, plus 4 electrons, producing 2 H2O and 4 OH. So I'm multiplying everything by 2. And you can see from the stoichiometry here, 1 oxygen is going to produce 2 hydrogens. So whichever test tube has twice as much gas, that's the one that's going to be hydrogen, because the stoichiometry of the reactions is producing twice as much hydrogen as it is oxygen. Good question for a multiple choice, wouldn't it? Right? How can you tell where the hydrogen is being produced, where you see the reduction? It's the one with twice as much. Another thing they can do here, this is pretty interesting too, they can put an indicator in here, because in this particular half cell, we're going to see this half cell here beginning to get very acidic. So we're going to see the production of hydrogen here. Over here, we're going to see the production of OH minus. Okay, let me just fix that up. Okay, so in here we're going to see the production of OH minus, and in here we're going to see the production of H plus. So if I provided an indicator, if I drop some, say, phenolphthalein in here, which turns colorless when it's acidic, or it would be pink when it's basic, what you would see is this test tube here would start to turn pink. So as this reaction proceeded with phenolphthalein, I'd start to see this test tube turn pink, because phenolphthalein would be pink in a basic environment. Get it? All right. So they could do things like this to say, okay, what's happening in that electrode? The electrode turns pink when it has phenolphthalein there, so you know that you're seeing the production of hydroxide on this side. All right. So I'm just going to write that in there. Okay, so we're going to see this guy becoming more basic, so this guy's going to turn pink. Now if I had some other indicator here, You know, depending on what the indicator was, you'd be able to look at that and be able to determine what's going on there. So as soon as you see an indicator changing color, you know that hydrogen or hydroxide is being produced or consumed, right, depending on what's happening there, and you can see it. Now, one of the problems with water as being electrolyzed, or the electrolysis of water, is that these are going to be representing non-standard conditions. Because remember, in order for us to use our redox table, standard conditions are going to be such that the concentration of all the ions are going to be 1 mole per liter. Now for pure water, we have to go back to our acid-base chemistry, and we have to recall the autoionization of water, because if we have pure water, technically speaking, that's all that should be in this test tube. All right? So what's going to have to happen here is pure water, we know, can do this autoionization thing where we get H3O plus and OH minus being produced here, in which case the Kw for that is minus 14, 1 times 10 to the minus 14. If we think backwards on this, or back to how we arrived at this number, that would tell us that the concentration of the acid would be 1 times 10 to the minus 7, and the concentration of the base would be 1 times 10 to the minus 7 as well. And that's nowhere close to standard conditions. And we know that because the pH of pure water is going to be a pH of 7. So because of this, we have non-standard values for the electrolysis of water. Let's go to your table and see what that means. Okay, 1 second here now. The electrolysis of water, what we end up seeing is that these would be non-standard values for pure water. Our table is calculating the values for E as if these concentrations were 1 mole per liter each. But we know full well that that's not the case for pure water. So what they had to do was calculate 2 new values in the case where we would use pure water. And here are the values, and I've listed those on your table, the one that I have written up here. And right here, see, this is the oxidation of water, and it has a standard value of 1.23, knowing full well that the non-standard value for pure water is going to be 0.185. So for pure water, the oxidation of water would end up being down here, right here. All right? So I've marked these on your table just to draw some attention to where they are. In the case of the reduction of water, that one's down on the bottom of the table, right here. And the reduction of pure water under standard conditions would be 0.83, negative 0.83. But we don't have standard conditions, so the non-standard value is negative 414. And that would end up being about right here, all right, for pure water. So you'd have to keep that in mind when we're doing some of these reactions. So let's just have a look at what this is going to mean for us. Okay, so if we have water in the container, like in the last couple of examples, we had pure sodium chloride, liquid, no water present, it was not aqueous. What would happen if we took a solution of an ionic compound and passed an electric current through it? Now we'd have to watch out for competing reactions, because it could be possible that it may be easier to oxidize or reduce the water than it would be to oxidize or reduce the metal ions. Okay? And what I'm going to do here is I've got something called the mountain range analogy, and the idea being that electricity always takes the easiest, simplest path. That's why, you know, you don't walk out on when there's thunder and lightning on wet grass or under trees, because the electricity is going to pass through you first, because you're an easy path. You know, you make sure that if there's electricity around, you're going to have rubber boots on so that the electricity won't pass through you. So the idea being here that if electrons are going to go from an anode to a cathode, they're going to take the easiest possible way. The electrons are lazy. All right? So when more than one way is possible, we have to be able to try and figure out which pathway is going to give us the smallest negative value. All right, so what we're going to do is we're going to write all the possible combinations, and whichever combination gives us the smallest negative value, that's the easiest path. Now remember, if we go back to our little diagram here of the little fellow here, you know, if there's only one path available, then that's where we have to push the electrons. All of a sudden, if I bring water in here and say, hey, no, hold on there, electrons, there's a shorter path. If you want to go from an anode to a cathode, there's a shorter path to take. The electrons are going to obviously take that lower energy path because it's less energy required. All right, so that's what we're looking for when we have mixtures. We want to take the lowest possible energy path. So here we go. Here's an example that says, predict the products of the electrolysis of 1 mole per liter lithium bromide aqueous. Now right off the bat, you might jump to conclusions here and say, okay, I've got lithium ions present, so that's going to be reduction. And I've got bromide ions present, so that's going to be oxidation. So we're looking at this and we're saying, okay, what's that voltage going to be? Well, if I work it out, doing a half-cell method, we're seeing that this guy is acting as the cathode. It's being reduced, and the bromide ions are going to lose their electrons to be the anode. That's going to take a negative 4.11 volts. Okay, good enough. But what we have to keep in mind is that we also have the possibility of doing the oxidation of water. And we also have the possibility of doing the reduction of water. So water could act as the anode, and water can also act as the cathode. So we have to look at this and say, is there an easier pathway to take? What we have to do now is do all the possible combinations. So I've already covered those 2 possible combinations. What I'm going to do now is I'm going to look at another situation whereby we can say, all right, let's take lithium as the cathode, but let's this time take water as the anode. So when I do this calculation, lo and behold, using the non-standard values, because we're dealing with pure water here, pure water, so we have to use the non-standard value, we get a negative 3.855. Hey, that's easier than that. So before this is going to happen, we're going to see this. So in this particular reaction, we may see the production of lithium metal, and we'll probably get the production of oxygen gas. In this example up top, we would have gotten lithium metal and bromine. But we're not going to see the bromine because it's easier to get oxygen. All right? Let's look at another situation where we can say, all right, let's look at bromine as the anode this time, and let's look at water as the cathode. So when we do this scenario, what we find is that, hey, easier again. The oxidation of bromine and the reduction of water is going to result in the production of bromine and hydrogen this time, which means before this is going to happen, or this, we're going to see this going on because it's a lot easier. So we're looking at this and we say, well, is there another possible way that we could do this? And the answer is, well, why can't we have water as an anode and water as the cathode as well? So what we're going to look at is say, let's do this reaction right here. And knowing full well that we have to do the non-standard values because it's pure water, we end up getting a voltage of negative 1.299. So we're saying, hey, that's easier again. So what we're going to see here is the production of oxygen gas and hydrogen gas on these 2 electrodes because that's the easiest way to go. So even though lithium and bromide are in the container, it's easier to do the oxidation and reduction of water. So in this container, you're not going to see any lithium being produced. You're not going to see any bromine liquid. You're going to see oxygen gas bubbling off one electrode and hydrogen gas bubbling off the other. Which is which? Hydrogen is going to produce twice as many bubbles, twice as much gas, and also if you want to add an indicator here, you're going to see that the 2 terminals are going to start giving us different colors under different indicator conditions, right? Depending what indicator you drop in here, one of the electrodes is going to be acidic, the other electrode is going to start turning basic. Okay? So there we go. So we got to watch out for that. Now you're looking at this and saying, well, if that's a multiple choice, that's an awful lot of work for a multiple choice. And it is, if we have to calculate all 4 possible combinations. There's an easier way to do this, and this is where you need your table. Okay, well, you need your table anyway because you've got to be able to figure out the voltage values. Here's an example where we're going to do the electrolysis of nickel chloride solution, AQ. So as soon as you see the AQ, you know that that's dissolved in water. So we're going to get some nickel chloride and water in a test tube. We're going to stick our 2 carbon electrodes down, and we're going to see how much voltage we need. So we can predict what we're going to see here. So what you're going to do is you're going to list every single species that's going to be floating around in that beaker, and we're going to get some nickel ions, some chloride ions, and you're also going to get water. Now, one of the things about water is we find that it's on both sides of the table. It can be an oxidizing agent, and it can also be a reducing agent. So remember, we've seen something like this when we did Bronsted-Lowry equations, when we said, okay, what are all the acids? List all the acids. What are all the bases? List all the bases. And then whichever acid is the strongest, whatever base is the strongest, that's the 2 we're going to use. Same thing here. We're going to look at our table and find out, okay, is nickel a reducing agent or an oxidizing agent? Well, let's go to our table. We look for nickel, and lo and behold, it's right there. Look. Nickel ions, not nickel metal. We don't have nickel metal. We have nickel ions. There it is. It's an oxidizing agent. So I go back to my list, and I would write down that, hey, nickel is an oxidizing agent. Now I search for chlorine. So I go back to my table. Chlorine is going to be way up the top here. Now you got to watch out because chlorine here is here a couple times. And what one you're going to get is this guy, of course, because it's going to be chlorine going to chlorine gas. That's the easier one to do. It's easier to do this than it is that because this guy is lower on the table. But in any case, chloride ion, it wants to get rid of that electron, so it's going to be a reducing agent. The chloride ion is going to want to be oxidized. So we go back to our little scenario here, and we're saying, okay, reducing agent. Now what we've got to do is we've got 2 possible reducing agents. We've got 2 possible oxidizing agents. Let's pick the strongest of each. The strongest meaning the easiest to be oxidized, the easiest to be reduced, the easiest path. So we go back to our table and we want to find nickel and water as oxidizing agents. So I would lift my table up again, and lo and behold, nickel as an oxidizing agent, water as an oxidizing agent. It's easier for nickel to be reduced than it is water because nickel is stronger. As we go up, we're getting stronger oxidizing agents. So this is my strongest oxidizing agent, so that's going to be my reduction reaction. I do the same thing with chlorine. I look up here and say chlorine and water. Oh, look at that. Water is stronger. Stronger is lower. So we're going to see water on one side, nickel on the other. So when I go back here, I would list this as my strongest oxidizing agent. I'm going to use that. This is my strongest reducing agent. I'm going to use that. So I rewrite this from the table. Nickel being reduced, water being oxidized, and lo and behold, we're going to see the production of nickel metal and oxygen gas. So you're going to see one electrode, you're going to start seeing a buildup of nickel metal. On the other electrode, you're going to see the bubbling of oxygen gas. Not only that, if I threw an indicator in here, the electrode that's producing oxygen gas is going to be producing acid as well. So if I had some indicator here that changes color in acidic conditions, I'll start seeing the change on this electrode. I would not see the change on that electrode because there's no acid being produced there. You're only going to see a color change around one electrode. There we go. The voltage necessary, well, now that we know our anode and our cathode, we can calculate it, and E cell ends up being a negative 1.07 with a slight overpotential to get this to work. Okay. Here's another example then. This one says predict the products of the electrolysis of sodium chloride. Okay, so this is different than what Davy did. Davy actually melted the sodium chloride to make it molten, 800 degrees Celsius. We're not going there. We're going to take some sodium chloride at room temperature, and we're going to make a 1 mole per liter solution of it. All right, so we're going to throw some sodium chloride in some water, dissolve it, stick 2 carbon electrodes down, and then say, okay, what are we going to see on each electrode? So we're going to do the shortcut method, knowing full well that it's sodium chloride is going to be producing sodium ions and chloride ions, and because it's an aqueous solution, then it's also going to be water present. Now you're going to check your table here, and you guys can go and check that on your table. You're only going to find sodium on one side, and it's going to be on the oxidizing agent side, way down on the bottom. We know that water can be an oxidizing agent as well. Chloride is only found on one side. It's on the reducing agent side. Water can be a reducing agent too. I check out and see, okay, which oxidizing agent is stronger? Is sodium stronger than water, or is water stronger than sodium? And the answer to that, of course, is that water is higher than sodium. So water is going to act as my oxidizing agent. And I simply write that off the table. H2O being reduced. Okay, H2O being reduced. Well, I think I already got this written out. There I go. Give me a sec. Okay, H2O being reduced to produce hydrogen gas and 2 hydroxides. And if we look at the other one, we can see that, okay, chlorine and water, it's going to be water, that's the stronger reducing agent. So we've got lots and lots of water present here. So we're going to see water acting as both. So both the oxidizing agent and the reducing agent. And of course, as a reducing agent, the water is becoming oxidized. Remember those terms? If it's an oxidizing agent, it becomes reduced. If it's a reducing agent, it becomes oxidized. So in this case, the oxidizing agent is water. It's becoming reduced. The reducing agent is also water. It's becoming oxidized. And what we're going to see here, we're not going to see any sodium being produced. We're not going to see any chlorine. We're going to see the production of oxygen and hydrogen in this beaker. Okay? This electrode, the anode, is going to start producing acid. The cathode is producing base. So again, if we threw an indicator here, this electrode is acidic, this electrode is being basic, so you're going to see the indicator changing accordingly. If you want to figure out the voltage for this one, we have to remember that this is pure water, so we have to use the non-standard voltages in order to calculate this. Okay? Now, if we did this, they would give you the non-standard values because they're not on the table. All right? I wrote them in for you on the table. They would not be there on the table, but if you needed them, hint, hint, wink, wink, nudge, nudge, they would be given to you. Okay? So there we go. So that's how we determine electrolysis of a mixture. Okay? Now, how could we do this in application? I'm just going to veer off on this in a minute here. I know we're running into a lot of time on this lesson, but what does that mean for something like Voisey's Bay, where we've got lots of nickel ore. So there's lots of nickel, and there's silver, and there's gold, and there's copper all mixed together in that particular slurry of what they're mining out of the ground. Okay, well that's coming to Placentia, where they're going to be having what's called a hydromet plant. And what they do is they chemically treat this, so that's why they would call it hydromet, because it's going to be a chemical reaction that occurs in water. And what they're simply going to do, this is oversimplified, we're going to talk about this in more detail later on, is that nickel ore that they're recovering up in Labrador, in Voisey's Bay, they're going to treat that chemically so that the nickel is aqueous, the copper is aqueous, and we're going to have some gold floating around here, and probably some silver, and probably some other metals ions. So what's happening is you've got a slurry of all these different types of metals. What they're going to do, of course, is they start to pass an electric current through it. So they're going to do an electrolysis. And when they look at the table, they'll look at this table and say, hey, which metal is going to be the easiest to reduce, or metal ion? And they're looking up here and we're saying, hey, if we pass an electric current through this, the very first thing we're going to get is gold, because that's the easiest thing to reduce. So any gold that's in that mixture is going to start being pulled to that negative terminal, right? That cathode, because it's going to be reduced. All the gold gets removed. Once all the gold is removed, then they go to the next step here, which now they're going to start seeing the electrolysis of, no, we're going to keep going down. Water is not a reducing agent, it is way down, but not up here. We're going to start moving down. All of a sudden, any silver that's in that mixture, now that's the next easiest step. So all the silver gets recovered, very pure, 100% pure. Any iron that might be present here is going to get converted to iron too. And then as we start going down, look, now we're going to start recovering the copper. So once all the gold is removed, and then the next easiest is the silver, and now we're going to start removing the copper because that's the next easiest step. And as we start going down through, we start to see, okay, tin and we start moving down nickel. Okay, now we're going to start recovering the nickel ions. And as we start moving down, we can see that whatever metal ion is there, it gets more and more difficult, but we're taking the metals off in terms of which one's the easiest, and then the next easiest, and the next easiest, and then the next easiest, and that's how it's going to work. Until eventually we get down here, in which case, if there's any aluminum or magnesium in that mixture, we won't get it. Because before we get to the aluminum or the magnesium, well actually it's going to be 0.414. So before we get to right here, we're not going to get any iron removed. Anything below that, and we're going to start to see the electrolysis of water. But anything above it is going to be recovered. Okay, because it's a lot easier to recover these metals up here than it is to do the electrolysis of water. These metals down here, easier to do the electrolysis of water than it is for these metals down here. And that's how it's going to work. All right, anyways, we'll talk more about that in the last lesson. But in any case, electrolytic cells, have a look at it in your textbook. Check some public exam questions here. Fire some off to your online tutor here, and fire a few questions off to me in the discussions. All right, see you later. Bye-bye.